Hello, Mr. Tom. So you inspired me to go a little deeper into the details of this circle and square method, and I have a confession to make that is actually not a good method. It's an interesting method, but it's not a let's say it takes a long time for it to converge, as you actually correctly found out when you tried to crank out the first 1,000 points or so using Excel, which you did completely correctly, and I'll get to that in just a second. So I put together something that's called a Python notebook. It's think of it as the cool kid on the block that's pushing BASIC to the side, but I think you'll be able to follow along. And I'll send you the like a PDF of it so you can see what I'm talking about. So this is what it looks like, these Python notebooks. So this is just about, let's see here. So just put a few kind of words in here. Some of it was copied from another notebook that I had been editing and putting together. So kind of a tutorial for people who are looking to learn how to use Python. And so first thing we do is just load a library of sorts. Second thing here, this part is picking random numbers. And so I just to show you how easy it is, I can call from the what's called the numerical Python notebook, call a random number. I'll call 100 of them, and then just plot them as circles. So there they go. I can do it again, different circles. Do it again, different circles, right? So that's like kind of one way you can do it. Anyway, it uses this Mersenne twister algorithm, etc., etc. Another thing that you can do is you can just pick from a normal distribution, and we can kind of see something like this. If it's normal, I don't know. Maybe that's interesting. But now let's get to the computing pi. So we can take random numbers. So we use this random.rand, basically taking a random points, and we'll select however many points. N points, we'll take 100 of them. And then to do just like you did earlier, we'll multiply it by 2 because it picks a number between 0 and 1. So it'll go from 0 to 2, and then we'll subtract 1, and that way from 0 to 2 it'll actually be shifted, and so it'll be from -1 to 1. So so just like you did. And then we'll define a radius, like you were saying. A radius is the x squared plus y squared, and then we'll just try to see, is it inside, yes or no, right? Okay, so that's kind of like what we want to do. And if we pick 1,000 points, we can see that the blue ones are the ones that are inside, right? So we say plot them as blue, all the ones that are inside of one, and plot them as red are all the ones that are outside of the circle. And we can increase the number, right? So I can do, instead of 1,000, do 10,000, right? But maybe one thing that you're noticing is 3.13 after 10,000 points, do 100,000 points. Now we have 3.14. It's so just to totally clue you into my absolute nerddom. When I was in high school, I tried to memorize the number pi to as many digits as I could. And I think I got it up to about 100 digits at some point. And people would come up to me at lunch and be like, "All right, do it. What's pi?" And I'd like start saying. And so I can still remember 3.14159265358979626634. Those are the numbers I remember. I was not reading that off of something. Do you believe me? And and so yeah. Anyway, total nerddom over here. Okay, so like one of the kind of summaries here is that, like, wow, 100,000 points, and we didn't even get the second digit. It rounds up to the second digit after the decimal place. You didn't even get the second digit. It's not very good. There's this other thing called Leibniz expansion of arctan, and I think that is actually what I was maybe thinking of when I was thinking about that Ramanujan method, which I put a little link here. And the Ramanujan is awesome, but man, this one is really simple, right? So you just take -1 to the k power, over 2k plus 1. And so k is 0, for example, you get minus 1 to the 0, which is 1, divided by 2 times 0, which is 0, plus 1. So you'd have, the first term would be, what, 1, and then you'd add that whole thing to minus 1 to the 1, which means that it'll now have a minus sign on there. And then you'd have 2 plus 1, so you'd have minus a third as your next term, and so on. If that doesn't make sense, I can write it out for you. But anyway, written as a for loop, which you probably remember from your good old days writing basic code, which I was also writing basic code back in the late 80s. We had a Tandy 2C computer, and it came along with this little booklet that had all these little codes in there. So I was busying myself in the basement writing basic code out of a book, probably at the same time that you were actually writing it for doing real world stuff. Anyway, this is pretty simple. You just basically, the total, we're doing a running total, keep adding up these next terms every single time, and then do it for k goes up to some number. If we run this, we get, well, 3.13 after, 100 numbers. We go up to, say, 10,000, we get 3.141, almost 5, right? So we get the first 4 digits. And of course, if we go up higher, we go to 100,000 digits, we're going 3.14158. Let's go to 1,000,000 digits. 3.14159, and then rounds to 2. So it's getting closer and closer and closer, right? Of course, if we keep adding on extra digits, okay, maybe it doesn't converge very quickly. Maybe I should have thought twice before doing that. That is 100 million points. How long does it take to do 100 million points in the for loop? Because I wouldn't have thought it'd be that long. Well, it took a long time. Let's take away 1 0 from this whole thing. Well, okay. So anyway, just wanted to show you that there are other methods, and those are kind of cool. Yeah, we'll come back to that one maybe and see how good it is. So now, I also wanted to show you loading in your Excel spreadsheet. So I can load this thing. Oh no, it's royally effed over here because I tried to run this giant thing. Here, we'll just restart. Yep, that's fine. I'll just load this notebook, or load the libraries, and then go back down to where we were here. Let's do something. There we go. Okay, so we got our 3.14159. That's pretty good. That's after 1,000,000 points. Let's take a look at your data there that you did. For example, if I oops, I called that as current. Let me do it as XS and Y, the X's and Y's. Okay. And so, for example, if we look at if we do a data file, this is the stuff that you sent me here, right? So test, these numbers. I guess I technically included this very first one in there. Oh well, no big deal. But I just wanted to kind of give you an idea of how I do these kinds of things programmatically. We already have defined your x's, xs and xy, and oh, the number of points is not defined here. Let me just pause real quick. Okay, so our remedy was just, I needed to look at what is the length of how many points did you choose. You chose 1,000, well, 1,001 because of that extra one, which was the test point, but we won't worry about that one right now. If I run this, you see that our approximation to pi is 3.07. So you actually did from 0 to 1, so you got 1/4 of a whole circle. Well, it turns out that doesn't really matter because it's going to be the same thing parallel across all 4 quadrants. So you got 1/4 of a circle, no big deal. The ratio of the number of points inside to the number outside is going to give you your approximation for pi. But it's bad, right? It's only 3.07. That's not so good. So I guess what we're learning is, let's say that we did 1,000 points up here. So I get 3.12, 3.13, 3.11, 3.16. I'm just trying it a few times. 3.19, 3.15. So I guess what I'm trying to argue here is that your number after 1,000 points, it isn't really that far off. It's actually totally reasonable result, actually. So the issue is that although this is an interesting visual way of doing things, a sum such as this is actually much, much more efficient. So as you can see here that we did this for loop. So anyway, hope that was interesting. I don't know. I wanted to show you something else actually. Let's see how easy this is to do here. Since I have your attention, this is one of the things that I've been doing over the apocalypse here. So this is an experiment here. This I have in my little home lab. This is called optical pumping, and we're basically. I'll show you the actual experimental apparatus in a second, but when I do that, it's going to change the temperature. So I'm going to show you the data first, and then I'm going to actually show you what's kind of under the hood here. So let's see how close I can get to this guy here. So you can see this is my oscilloscope. Probably getting a little glare off the screen there. Okay, that's my oscilloscope, and I'm scanning a magnetic field. Let's see here. Here we go. I'm going to scan a magnetic field here. Oop, need to go a little bit further. There we go. Okay, I'm going to scan my magnetic field, and what you're actually seeing here as I scan is I'm actually getting these little dips in the light. And so what you're seeing is all the light's going through, and then as I hit this resonance, as I hit the resonances over here, the light is actually dipping down, and we're not getting as much light through. And so now I'll show you what we're actually looking at here. Maybe this is something out of like a old science fiction movie or something. But we have here a light source that's actually producing infrared light, and it's going through some lenses and optics, and then finally it's going into a cell which is inside of here, which is temperature controlled, and there's rubidium atoms inside. And when the light goes in, these rubidium atoms will interact with the light based on whether or not there's a magnetic field present. And that's where these coils come in, is that we actually use the coils then to change the magnetic field, and then as we scan through the magnetic field, we hit this resonance condition, and the atoms are saying, okay, yeah, we're going to interact with the light. And so then in our detector on the other side here, which is right here, that detector is actually going to then register a little bit less light going through because we've hit this resonance condition. Anyway, I just thought you might find that interesting. This is not something for my research, but it's a topic that we teach our undergrads as we instruct them on how to do spectroscopy in our advanced lab series. It's been an experiment that I've coached students through, but I haven't actually really taken the time to sit down and do it myself from scratch and go through all the different experiments that sort of flesh out all the details. So my chair was kind enough to let me bring this home during the shelter in place. So it's given me another fun thing to do while I'm, just trying to take care of myself and hanging out at home. So anyway, I hope you enjoyed, Tom, and I'll talk with you later.